Okay, so while we're waiting for Adobe Acrobat to finish updating, which it just decided to do, I want to talk a little bit about a concept called fitness. You hear Darwin's theory of evolution described a lot as survival of the fittest. I hate this expression and I begin uncontrollably twitching every time somebody says it. And there's a couple of reasons for that. One is that Darwin didn't actually say it. The phrase was coined not by Darwin, but by a Victorian era philosopher by the name of Herbert Spencer, who has gone down in history as one of the most boring individuals ever to live, who incorporated a version of evolution into his own grand theory that basically explained how the entire universe had begun as a completely homogeneous mass and evolved into Victorian Britain, which of course was the highest possible summit of human existence. So it's not something Darwin actually said, but more importantly, whenever you talk about evolutionary fitness, people immediately think of survival of the meanest. If I say survival of the fittest, people are likely to think of, a savage, ruthless pride of lions tearing apart a helpless gazelle on the Serengeti plain, or a savage great white shark ruthlessly tearing apart a innocent baby seal on Shark Week, on Animal Planet, whatever it might be. That's got very, very little to do with fitness when we put it in an evolutionary context. And you'll hear people saying survival of the fittest in an attempt to either justify or to argue against this view that everybody is only out for himself and it's only the cruel and the ruthless and the strong that survive. That is emphatically not true. There are many times, lots of them, we'll talk about this coming up later, when it's actually the most cooperative that survive. There are lots of ways that altruistic behavior can be favored by natural selection. Happens all the time. And again, we'll be looking at that more closely in a few weeks. The other thing is I've had to field counter arguments from various people, including someone who used to work over in computer science, who you'd think might know better, that the phrase survival of the fittest is meaningless because you define the fittest as those who survive. And these survivors are the ones that are most fit, so you're not really saying anything. You're not adding anything new. It's a statement that's called a tautology, where we already know that the subject is exactly equal to the predicate. The way I try to explain this that gets around all of this is to have you think about your car insurance for a minute. Now, insurance companies, if they could predict the future, like if they had, these strange beings floating in a tank who could see the future in that weird movie a few years back, the one based on that Philip K. Dick story, I can't think of its name. If they could do that, they would be absolutely perfect because they would charge you a very reasonable rate for car insurance and then suddenly jack up your rate to $1 million 5 minutes before you had that accident. If they could do that, they'd be sitting pretty, but they can't see the future. Nobody can. There's no way to tell in advance that on March 15th of this year, you'll get T-boned while making a left turn from Donaghy onto Dave Ward. Mind you, I hope you don't, but they can't make a precise prediction like that. They don't know when you're going to have an accident. What they try to do is calculate your relative risk of having an accident based on what kind of driver you are, right? They cannot calculate the probability that you will have an accident, but they can calculate the probability over the class of all, I don't know, 20 to 25-year-old male drivers of used Toyota Camrys in the state of Arkansas that drive less than 100 miles a week or something like that. They'll divide up all of their clients into classes like that and calculate the probability of having an accident using data from all members of that class. So they'll take the class of all people who are younger than 21 and own red Corvettes and have 3 or more speeding tickets, and that's one class. And to that class, they will probably assign a higher probability of having an accident than the class of all people who are 45 to 55 and own sensible minivans and have not gotten a speeding ticket for 5 years. Okay, so you divide drivers into these classes. You can calculate the probability that any given one will have an accident over any given length of time and use that to set your auto insurance rates. That's not based on your individual behavior because you can't calculate the probability of a single event. I can't calculate the probability that you will have an accident at 4:34 p.m. on March 15th, making a left turn from Donaghy onto Dave Ward. That will either happen or it won't. But you can't calculate the probability of a lone event. What you can calculate is probability of a class of events. Now, those can be wrong. You could be an 18-year-old with a red Corvette with 3 speeding tickets already and still never get in an accident. I mean, you could just be extremely lucky or extremely skilled or smarten up and get some sense and learn to obey posted speed limits. So you could be a cautious middle-aged driver in a minivan who's never had an accident in his or her life, and then just suddenly decide one day, what the hell, there's a pandemic on, screw it, and slam the pedal to the metal and start screaming towards Valonia at 90 miles an hour like the Ride of the Valkyries and get into a terrible pileup. You know, it happens. People occasionally lose it. People can be unlucky. You know, you could be the most careful driver in the world and somebody else hits you when you're the one that's not at fault. You can say the same thing about lots of other things. You know, I've known people who smoked 3 packs a day all of their lives and then, you know, died of something completely unrelated to their lungs at the age of 97. You know, there's always people like that. And there's always people who, you know, there's a few people who don't smoke, take very good care of themselves, and still die young of a heart attack or lung cancer or something like that. That does happen. We don't have certainty in life, but you can assign relative risks based on the class of individuals that somebody belongs to. And it's not always perfect, but it is the way that insurance companies make their money because they know how to set your premium based on the class of drivers that you're assigned to. And my way of thinking of fitness in an evolutionary sense is that it's just like that. You can't, how do I want to put this? You can't calculate the fitness of an individual person. There is no meaningful way that I could say that I am more fit than you. First of all, fitness is not based on survival so much as it is based on reproduction. I could have the most freaking awesome genotype that has ever been invented for the human species and still get hit by a bus before I get to have any kids. Somebody could have the dorkiest genotype that has ever evolved in human history and still find somebody that loves him and has his babies. There's no way you can assign fitness to an individual. Fitness is a property of genotypes. You can't say that I am more fit than you. What I could possibly say is something like the class of all people who share a particular genotype with me are more likely to have surviving offspring than the class of all people who do not share that genotype. So you calculate it over classes, you don't calculate it over individuals. All right, I'm going to go ahead and pause there and see if I can't bring up the practice problems, and I'll show you how we actually calculate this. Okay, so that's practice problem 7 in your set, and this is a true story. A geneticist named W.H. Goddard was an early advocate of eugenics, and he suggested that what he called feeble-mindedness was caused by Mendelian inheritance at a single locus with 2 alleles, the same basic setup as purple or white flower color in peas. People who were homozygous dominant, which we can write here as capital F, were of normal intelligence. Heterozygous people were of normal intelligence, but they were carrying the feeble-minded gene. And then anyone who was homozygous for the feeble-minded allele, which we can abbreviate as little f, were, as Goddard said, incapable of managing their affairs with ordinary prudence, unable to take care of themselves. This is really not true. There are types of mental deficit that can be inherited genetically. There are some disorders of brain development that do have a genetic basis. There are certainly things like fetal alcohol syndrome comes to mind that are pretty much entirely environmental, so are types of brain damage. And Goddard's definition of feeble-minded includes everybody from people with genuine cognitive deficits to people of ordinary intelligence who are just scatterbrained and make bad choices. Goddard ran a state hospital for the feeble-minded, I want to say in Massachusetts, because back in the day, people with mental illness were segregated from their communities and often sent to state institutions where they might be locked up for years. Arkansas used to have one of these. If memory serves, it was over in Dardanelle, if you know where that is. And Goddard, being the superintendent of one of these, was supervising everybody from people with genuine developmental delay to people like girls whose mothers remarried and whose stepfathers didn't want to be bothered with them. It was fairly easy to get a judge to get them declared feeble-minded, pack them off to an institution, and then the stepkids are all out of the picture. That used to happen. So anyway, for the purposes of working this problem, pretend that Goddard's was right, that there is some kind of feeble-mindedness that's governed by a single Mendelian gene with 2 alleles. We're in backwards world now. And let's assume that in backwards world, Goddard was right. And we're going to assume that we're in some kind of horrible dystopia, and there's a federal government agency dedicated to tracking down and sterilizing everybody who is feeble-minded. If you are feeble-minded, you get your tubes tied. There used to be laws on the books in 30 states that did mandate the surgical sterilization of the feeble-minded, and there were groups in the 20th century that were lobbying for this nationwide, that wanted a constitutional amendment giving the government to tie your tubes if they thought you were stupid. A very good thing that that didn't come to pass. But let's imagine that we're in the world of The Handmaid's Tale, and something like that did really, is a reality. Now, the first part, this is kind of a throwaway part of the problem. According to the 1910 census, the population of the US was about 91.9 million. Goddard estimated that 1% of the population was feeble-minded. Assume that the population is in Hardy-Weinberg, calculate the allele frequencies, and then the percentages of the population that would be heterozygous and homozygous dominant. Okay, I'm summoning up the whiteboard. First of all, this was a test question, and I threw that population figure as a red herring. You don't actually need to know. It doesn't matter what the US population is. But we will say that we have, people that are FF are normal, big F, little f, normal, but they're carriers. And people with little f genotype are feeble-minded, are dopes, dummies, and dimwits. Let's say that 1% of the population is feeble-minded. We can write that as a decimal. That's a proportion of 0.01. Assume the population is in Hardy-Weinberg. What's that mean? That means that if a population is in Hardy-Weinberg, there's a direct mathematical link between allele frequencies and genotype frequencies. And that link is specifically that the frequency of one heterozygote is going to be, or one homozygote is going to be p squared. That's the frequency of the allele squared. Frequency of heterozygotes is going to be 2pq, 2 times the product of the allele frequencies. And the frequency of the other homozygote is going to be the square of its allele frequency. Okay, now we happen to know what the frequency of the feeble-minded is in this dystopia that we're working in. It's 0.01. What that immediately tells you is that Q is equal to the square root. Okay, what happened here? Q is equal to the square root of 0.01. It's equal to 0.01 with this thing on it, because I can't figure out how to type a square root symbol at the moment. So that's easy. The square root of Q, or the square root of 0.01, square root of 0.01, and it happens to be equal to 0.1. P is 1 minus Q, so that's equal to 0.9. If we're in Hardy-Weinberg, the frequency of individuals that are homozygous normal is p squared. That's equal to 0.9 times 0.9, 0.9, and that is, of course, equal to 0.81. And the frequency of heterozygotes is 2pq, and that's equal to 2 times 0.9 times 0.1, and that's equal to 0.18. And then the frequency of homozygous recessives, the feeble-minded, we already know what that is. It's 0.01. You can check your arithmetic by adding these three and see if they all add up to 1. They should, and in this case, they do. I tell people they can check their arithmetic by adding up these frequencies and seeing if they sum to 1. Some people get confused by that and try to add those as a test to see if the population is in Hardy-Weinberg equilibrium. No, this is not, the fact that these add up to 1 does not mean that you're in Hardy-Weinberg. The fact that these add up to 1 means that you have done your math correctly. That's all. So there is 7a. If we were in backwards world where there was such a thing as feeble-mindedness that was inherited this way, then these would be the genotype frequencies if we assume the population was in Hardy-Weinberg equilibrium. Now, just for fun, remember what that means. It means that the United States would have to have, well, the population would have to be large. 91 million is certainly large. There would have to be no selection and random mating, meaning that feeble-minded people were just as likely to survive and have offspring as normal people, and no sexual selection would be happening. Feeble-minded people would not have any different odds of finding mates. Would also have to mean no mutation, although, as I've said, realistic mutation rates don't do very much to push a population out of Hardy-Weinberg. And there'd also have to be no immigration, which we know is violated because this is the time Goddard was working was a time of very extensive emigration coming to the US from Europe. So we might be suspicious as to whether the population really is in Hardy-Weinberg. But if it is, those would be our allele frequencies, and they would be linked to the genotype frequencies by these equations that I drew down there. Okay, not a very good circle, but you get the idea. Okay, let's go ahead and clear that. And going back to the this, as we mentioned, 30 states had laws at one time that mandated surgical sterilization of the feeble-minded. There were organizations that were lobbying to make that a nationwide law. There was a landmark Supreme Court case, Buck versus Bell, that established that these laws were in fact constitutional. It's not one of the Supreme Court's prouder moments, but that is the current legal precedent. So imagine that we're in the Republic of Gilead or some kind of alternate reality dystopia, and the US really did put into effect a nationwide sterilization law, and assume that there is some government agency, call it what you want, I don't know, the National Bureau of Tying Tubes or something, and assume that the authorities are so efficient that they never sterilize anybody who's not feeble-minded. This is completely unrealistic because, as I mentioned, Goddard's definition included a lot of people whose minds were perfectly normal, who might just be in the wrong place at the wrong time or something like that. but assume that they never, ever, 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 ever sterilized anybody who wasn't feeble-minded. And they tracked down and sterilized 90% of the people who were. Okay, what would be the frequencies of genotypes and of alleles after one generation of this? All right, let's go back to the whiteboard. Okay, so it goes like this. The probability that the probability of somebody dying without having kids, well, kids that also survive, is some number. It doesn't matter what it is. I'm going to call it X. You know, anybody, regardless of genotype, could die young of, you know, some disease that strikes at random. You know, this is before vaccinations, so regardless of genotype, somebody could always die of polio or die falling down a well or you know, something like that. There's lots of total rando reasons why people could die. Somebody could also live a full life, but just never find the right spouse and die childless. Somebody could live a full life, but not be interested in having children for any one of a number of reasons. Somebody might live a full life and just be really unlucky or get his or her heart broken. Or somebody could marry, have kids, and the kids all die young of scarlet fever or something like that. Things like that happen. So for anybody, regardless of whether you are feeble-minded or not, there is some probability that you do not get to pass on your genes. Okay, with me there. The probability of somebody with the feeble-minded genotype dying without having surviving kids is equal to the probability of them dying anyway times 0. Okay, times 0.9. Okay, because they have a certain probability of dying without having kids. They also have a 0.9% chance, a probability that's 9 in 10 of getting tracked down by this imaginary federal agency that we have and getting their tubes snipped before they can have kids. So the probability that somebody will successfully have kids is 1 minus X, right? The probability of somebody with the little f genotype having kids is equal to same probability as the people who are not feeble-minded multiplied by 0.1. Okay, got that? Remember that the probability of two things happening is the product of their probabilities. 1 minus X is the probability that somebody will have kids, that anybody will have kids, any person that you pick will have kids. if someone's feeble-minded, you have to multiply that by 0.1 because that's the probability that they will have kids multiplied by the probability that they won't get their tubes tied by this evil federal agency. Okay.
Can I ask you a question?
Shoot.
Why is it multiplied by 0.9 in the somebody's who's homozygous little f dying without surviving kids?
Oh, because in addition to the probability that they are going to die without surviving kids for some reason unrelated to this problem, there's a 9 in 10 chance that this mysterious federal agency is going to snip their tubes. So it's
Oh,
the
okay.
probability of anybody dying multiplied by the probability of, wait a minute, I think I did that wrong. Hang on. Because if they die of something else, they can't get their tubes snipped. Okay, the probability of one thing or another thing happening is actually the sum of the probabilities.
Okay.
Okay, thanks for catching me on that.
You're
Okay,
welcome.
right. What we want to do now is get rid of those x's because I have no earthly idea what x is. So what I can do is this. The probability of somebody who's big F, in other words, normal intelligence, divided by the probability of anybody at all having kids is equal to 1 minus x divided by 1 minus x. And that's equal to 1. That's not a probability, that's a probability divided by another probability. The x's all completely cancel out, and we can assign, and we're going to call that W subscript big F. The probability of somebody who's heterozygous having kids divided by the probability of anybody having kids is equal to 1 minus x divided by 1 minus x equals 1. And we can call that the fitness, abbreviated W, of that genotype. And the probability of somebody who's little f having kids divided by the probability of anybody having kids is equal to 1 minus x times 0.1 divided by 1 minus x. 1 minus x's cancel out, and that's 0.1, and we call that W little f. Okay, so those W's that I calculated are not probabilities per se, they're relative probabilities. They are saying, assigning the genotype big F a W of 1 doesn't mean that everybody with the big F genes is guaranteed to reproduce. What it's saying is that relative to everybody in the gene pool, they have the highest probability of reproduction. The simplest way to calculate fitness doesn't even involve all that probability stuff. I went through it to try to clarify what you were doing, but you could just calculate, let's say, the average number of offspring for 3 genotypes and divide them all by the highest. And so what you're saying here is not that if you have the big F genotype, you're guaranteed to have kids. It's saying that if you have the little f genotype, the probability that you're going to have kids is only 1/10 the probability of somebody who's big F having kids. Right. The raw probabilities are still not necessarily equal to 1. You could have the big F genotype and never have kids for any number of reasons that aren't really relevant. What it's saying is that if you have the little f genotype, the probability of you having kids is 1/10 the probability of anybody else having kids. So these W's are not really probabilities, they're probability ratios. Okay, now that I have made that clear as mud, if we go back and look at the problem, what would the frequency of genotypes and alleles be after one generation? Well, let me see here. Okay, I'm going to clear the whiteboard. All right, in the population, if we are in Hardy-Weinberg, then the frequency of equals Q squared. The sum of all of those is equal to 1. So we can write P squared plus 2PQ plus Q squared equals 1. And that ought to look familiar. That is simply what you get when you square P plus Q. Right? If you have P plus Q and you multiply it by P plus Q and you expand it, that's what you get, right? You do first, outer, inner, last, like you learned back in 8th grade algebra. Okay. If we want to see how fitness works out, we have to introduce something else. If you're throwing in fitness, we have to add a term that will show us that some of these genotypes have a relatively greater or lesser chance of reproducing than other genotypes. How do we do that? Well, we expand it by doing P squared times W big F. Okay, P squared would be the would be the frequency of the genotype if we were in Hardy-Weinberg. But we're not in Hardy-Weinberg because selection is going on. So since we have selection going on, the equation we want is P squared times W big F. That is the frequency of homozygotes if the population were in Hardy-Weinberg times a number that expresses how much it's not in Hardy-Weinberg. And then the next term is 2PQ times our W associated with the big F little f genotype. That's 2PQ is the frequency of heterozygotes if we were in Hardy-Weinberg, multiplied by a number that expresses the fact that we aren't in Hardy-Weinberg, plus Q squared times W little f, which is Q squared is the frequency of homozygous recessives if we are in Hardy-Weinberg, multiplied by a number that tells you that it's not in Hardy-Weinberg. If we add all those up together, we get a number that is not equal to 1, and we write it as W bar, which is a W with a bar over the top. There's my attempt at drawing a bar. A bar over a letter typically means it's a mean. So W bar right there is what we call mean fitness of the whole population. So if we want to calculate W bar, we can plug in our numbers, and that's the first thing we want to do. So W bar, there's our bar, is going to be, okay, P is 0.9, is going to be 0.9 squared, 0.9 times 0.9 times the fitness, which is 1, times the fitness of that genotype, plus it's going to be 2 times 0.9 times 0.1 times 1, which is the fitness of that genotype, plus 0.1 times 0.1 times 0.1. Right? That first 0.1 times 0.1, that's Q squared. But then we have to multiply that by another 0.1 because that 0.1 is the fitness of the little f genotype. Right? If all of our fitnesses were equal to 1, we would just have this equation over here. They'd all drop out and we'd be in Hardy-Weinberg land. The fact that those fitness values are not all equal to 1 is the way you model selection taking place. And if we calculate this, what we get is W bar. That should be equal to 0.991. I think I've got that. Anybody who feels like checking, go ahead and check that. Okay. Now what? What we have to do now is predict the genotype frequencies after one round of selection. And the way that we do that is we take this equation that we derived, we take this, and we divide every term by W bar, right? So we divide P squared times W big F by W bar, and 2PQ times W big F little f by W bar, and 2 squared times W little f by W bar, and W bar by W bar, which gives us 1. Okay, let me see if I can break that down. If we're in selection, then after one round, the new frequency of homozygotes is going to be P squared times W big F divided by W bar. There's that bar. Okay. To visualize that a little bit better, we can write the same thing. We just need to do it, just group the terms in a slightly different manner. Dang it. Okay, that's equal to P squared times W big F divided by W bar. There's the bar. Okay, think about this. P squared is the frequency that of the big F genotype that you would have if there wasn't any selection going on. Okay, so we've got this frequency, we've got what would happen if there was no selection going on, but we're multiplying it by this, W big F divided by W bar. If the fitness of the big F genotype is greater than W bar, then that quotient that I've just circled is going to be greater than 1, right? If the numerator's bigger than the denominator, right? If the number on top is bigger than the number on bottom, then that's greater than 1, right? So the frequency of the big F genotype is going to be the frequency that it would be under Hardy-Weinberg multiplied by something that's either greater or less than 1. If it's greater than 1, well, you're multiplying the genotype frequency under Hardy-Weinberg by something that's greater than 1. That just tells you that the frequency of this genotype is going to be larger than it would be under Hardy-Weinberg. The number is going to increase from one generation to the next. In fact, let's go ahead and calculate that real quickly. So the frequency of big F is going to be 0.9 times 0.9 times the fitness of the big F genotype is 1. W bar is 0.991. So think about what I've just put in brackets right there. 1 divided by something that's less than 1 is going to give you something that's greater than 1, right? The numerator is, the number on top is big, the number on the bottom is small, the numerator is greater than the denominator. That fraction is going to be something bigger than 1. So what this is telling you is the frequency of big F homozygotes after one generation is going to be larger than it would be if you had no selection and all fitnesses were equal. How much larger? We plug and chug, and this is going to be equal to something like 83% or 0.83. Anybody got that? Anybody quicker with a calculator than I am? Uh, 0.81, Thomas says. Okay, great. That's going to be, where'd my meeting go? There's the whiteboard. Wait, are you sure about that? 0.9 times 0.9 is 0.81. But then you're multiplying it by something that's a little greater than 1, so it ought to be just a little bit larger than 0.81. Okay, Mackenzie says she got 0.817. Great, it's not much, but we'll go with it. 0.817. Okay, so our frequency of individuals with the big F genotype over one generation of the government agencies tracking down the feeble-minded and snipping their tubes is going to go from 0.81 to 0.817. Not a very big change. Okay, our frequency of heterozygotes is going to be equal to 2pq times W times the fitness of that genotype divided by W bar. There's W bar. Okay, what's that going to equal? Come on, I'm sorry, I'm having a hard time getting the cursor where I want it. Yeah, I think I'm the cursor right now. And that's going to be equal to 2 times 0.9 times 0.1, which is what the frequency would be if there wasn't any selection. And then it's multiplied by 1.0 divided by 0.991. That ratio right there is the effect that selection has on the genotype frequency. So 2 times 0.9 times 0.1 times 1 divided by something a little less than 1 is going to be a little bit more than 0.18. It's going to be like 0.18. I want to say it's 0.182. Okay, great. Thank you, Thomas. 0.182. And then finally, and I think I have just enough time to do this before we have to call it a day, the frequency of little f is going to be q squared times fitness of little f genotype divided by W bar. W bar, there's the bar. Okay, and that's going to be equal to 0.1 times 0.1 times the fitness of that genotype, which is 0.1, divided by W bar, which is 0.991. So 0.1 times 0.1 would be the frequency of individuals with this genotype if there wasn't any selection. We're multiplying it by a term that tells you what the effects of selection are, and 0.1 divided by 0.991, the numerator is greater than the denominator, that's less than 1. So this is telling me the frequency of little f individuals is going to be less than it would be if there was no selection, which seems reasonable. And if you plug and chug that in, you ought to get about 0.001, I predict, or very close to it. Okay, that's your answer. We have, okay, Mackenzie's got it, 0.001. Thank you. That's our answer right there. If we lived in this, nightmare utopia where anybody feeble-minded got their tubes tied and nobody who wasn't feeble-minded got their tubes tied, then after one generation of this program, we would go from having 81% of the population with the big F genotype to 81.7 of the population percent with the big F genotype. And we go from 0.18, 18% of the population being carriers, to 18.2% of the population being carriers. We would get the frequency of feeble-minded individuals down from 1% to 0.1%. So I guess there's that. Notice that it would not have numerically that great an effect. You're doing this huge program and it doesn't really enormously change the allele frequencies. And that's an answer to a much earlier question that one of you asked. Selection is not that effective at getting rid of alleles when the alleles are already very rare. We might have a chance to come back to that point. But it being 12:05, I'm going to go ahead and stop recording, but I hope you see how we can calculate and use fitness. And on Thursday, I'll work a couple more problems using fitness, and maybe we can move on to inbreeding, and that'll be most of what I want to cover in this first third of the course, although we'll keep going a bit before the exam. So I'm going to go ahead and stop the recording now.